In this video, we discuss the magnetic field generated by a current carrying wire and the field generated inside of a solenoid or a coil of wire. We begin with the current carrying wire, and the magnetic field generated by this wire is really interesting. It swirls around the wire according to a right-hand rule. You put the thumb of your right hand in the direction of the current, and your fingers on your right hand will curl in the direction of the field. The strength of the magnetic field around this wire, of course, drops off as you get farther away from it, and this is quantified by Ampere's law, and that's mu naught I over 2 pi r, where mu naught is called the permeability of free space, and it's given by 4 pi times 10 to the negative 7 Tesla meters per amp. You can verify the units make sense real quick by plugging into the formula. Mu naught has units of Teslas in it, but I have to cancel 1 unit of amps because of this I here for the current, and I have to cancel the meters in the denominator from this r, which is the separation distance from the wire. So the meters and amps cancel out, and I get Teslas. Note that the definition of mu naught changed very slightly in 2018, which changed it about 9 decimal places in, but we're going to stick with this traditional 4 pi times 10 to the negative 7 because it's easier to remember. In our example, we want the magnetic field strength and direction at a distance of 50 centimeters above and below the wire shown below. So I put a 2.5 amp current through this wire, and I need the magnetic field direction above and below the wire, and that's done with the right hand rule. I put my thumb in the direction of the current, the field wraps around in the direction of my fingers, and so directly above this wire my fingers are poking out of the page. So my magnetic field is outward, and then below the wire the magnetic field is diving back in to the page. And we use X's for that. As for the magnitude, we use Ampere's law for this, and we just plug in the numbers, 4 pi times 10 to the negative 7, a current of 2.5 amps, divided by 2 pi times the distance from the wire, which is half a meter, and we get 10 to the negative 6 Teslas for this field. On the right side of the screen, we're talking about the field generated by a solenoid, so this is a perfect cylindrical coil of wire. I've shown the current running down the face that's closest to us, which means it's running up the face that's farthest from us and coming out of the page at the top of the solenoid and into the page at the bottom of the solenoid. So to get a better sense for what's going on, in the second picture I slice the whole thing in half, and I can see that current going into the page all along the bottom of the solenoid every time a wire dives through the plane of the page, and the current's coming out at the top of the solenoid. Now what I've done in the picture is I've applied the right hand rule at all those points where the current's going in or going out. So if I apply the right hand rule to these inward currents, I put my thumb into the page and my fingers curl in the direction of the field around each of those wires, and that's what all these little loops are. Same for the top of the solenoid. I put my thumb out of the page and my fingers curl in the direction of the field, so that's what all these little loops are. Now we're not interested in the field outside of the solenoid. Actually, if the solenoid is very long and skinny, the field outside is very nearly zero. What we're interested in is the field generated inside the solenoid. And I can see from all of these little loops around the wires, all these little contributions. Along the upper edge, those are all pointed rightward with a little bit of extra tilt. And I can see that where one of the loops has a little upward component, like right here, the other one next to it will have a little downward component, and those actually cancel out perfectly. And it leads to an exactly rightward pointing magnetic field inside the solenoid. And in fact, you can prove that it's a constant field. So even in the middle of the solenoid, it has exactly the same strength as it does toward the edges where the wires are. So there's the constant magnetic field inside the solenoid. At the ends of the solenoid, you will see fringing. And that fringing looks very much like the field of a permanent magnet made of iron or some other ferromagnetic material. And in fact, that's why a solenoid is called an electromagnet. This is just a way of electrically generating, with a coil of wire, a field that looks just like a permanent magnet. And this has a lot of advantages because you can just flip on a switch and turn it into a strong magnet. But when you don't need it to be a magnet, you just turn off the switch and it's not a magnet anymore. Now the strength of the field inside the solenoid is given by this little formula, B equals mu naught Ni, where mu naught is the permeability of free space that we defined back here. I is, of course, the current through the wire, and the little n deserves some explanation. It's actually the number of coils per unit length. In other words, coils per meter in the solenoid. I could also call it loops per meter. So if you double the density of the loops in your solenoid, maybe wrap 2 layers of loops on top of each other, then of course that would double the field inside the solenoid. Let's do a quick example. I have a solenoid formed by wrapping 1,000 turns of wire on a 5 centimeter length. That allows us to calculate the little n. So I have 1,000 turns or loops on a length of 0.05 meters. I simplify that to get turns per meter, and that's 20,000 turns per meter. Then I want the field strength inside the solenoid if we run 0.25 amps of current through it. So I just plug into B equals mu naught Ni, and that's 4 pi times 10 to the negative 7, 20,000 for the turn density, and then 0.25 amps for the current. And I get 0.0063, just keeping 2 sig figs, Teslas, or I could call this 6.3 millitesla. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.